All right. Hello, everybody, to the penultimate IFT 372 study session. So again, as my announcement said, these study sessions are primarily going over questions for the final practice, just to prepare you and help you study for the final exam. And again, for the final exam, it's available now. You have until Monday midnight, so 11:59 Arizona time on Monday to complete it. You have to complete it all in one sitting, so when you sit down and start taking it, make sure you're committed to it. And again, we've had some time to look at the final discussion now on your own individually, so hopefully you made a crack at it and gotten some idea of what you're going to be looking at and have some area where you know what you're comfortable with. But there is still discussion happening in discussion board, so feel free to post there and contribute to that discussion with some of your questions, and hopefully we'll get some of them worked out now. So for those of you who haven't attended these study sessions before, generally I don't have much of a structure to them. It looks like there's only a couple people watching right now, so I'll wait for a couple minutes before we really get going. But these sessions are generally here for you to have your questions answered, so I generally rely on you guys to help contribute with questions. So again, the focus for this session is mostly going to be on the final study guide, but if you have any questions related to that, then let me know and we can tackle them. Hello, Ryan. So again, we'll wait just a few more minutes to have some more people give some more time to show up. And I think I saw, Ryan, you made a few posts in the discussion board too, so I'm keeping an eye on those. I haven't managed to contribute to them quite yet today, but I'm hoping to do so after the session's over. But if you have answers for your classmates as well, please continue to contribute. Ryan says, let me know if I spread information. Yeah, and that's what's, if you spread misinformation, and yeah, that's what we're going to be doing. So I'll get an eye on that. I'm sure you're fine. If you were confident enough to post, I'm sure you're comfortable with it at least. But I know Dr. Helm and I will be keeping an eye on that. And that's why we prefer you guys to study or converse in places where we can see it, because we don't want people to be getting confused with their own information. So you're free to obviously meet on your own time and do things, but we would prefer it for the benefit of the class. It's generally better to have that discussion where Dr. Helm or myself can take a look at it and say, okay, well, it's not quite right, and we want to nip any errors or mistakes in the bud before they get rooted in truth. Okay, we have a couple people here now, so we might as well get started. And again, we can wait for other people will show up or not as we continue. So let's go ahead and get started. If anybody has any questions they want to kick us off with. Okay, so Ryan's going to start us off with number 20 on the practice final. So let's take a look at number 20. Okay, so number 20. Okay, great, Ryan's copied it for me, so that's handy. So here's our problem for number 20. How many equal energy users can a CDMA system support if the received power of each user is 4.77 dBm and the total interference power is 19.1 dBm? And so Ryan's found a formula. One second, let me just make sure I'm on the same page. And so you have your formula there, Ryan. Are you just checking to make sure that's the correct formula for the problem? Maybe jot down Ryan's formula. Yeah, and whether the answer should be rounded down. Okay. So yeah, that is the correct number. So we have interference power equals number of equal users minus 1 times received power per user. And so this is what we're looking at for, and that is the correct formula to use for this problem because it addresses everything we need to solve for, basically. We're given interference power. Total interference power is 19.1 dBm. We're trying to find the number of equal energy users, and we're also given received power of each user is 4.77 dBm. So these are all the units we need, and we're solving for the correct thing. And so if we plug in all of our numbers, so we have interference power is 19.1 dBm equals x minus 1 times 4.77 dBm. Now remember, this is a decimal equation, so we can't use decibel values. We'll have to do the conversion. Yeah, and so, okay, Stephen's asking the question right now, does this have to be done in decimal using that equation? Yes, it does, because we're subtracting 1 and multiplying. So this is a decimal equation, so we can't just plug in decibel values like I was saying. We have to do a conversion to decimal. And so if we do that conversion, we have 81.283 equals x minus 1 times 2.999. And then from here, we're just solving for x, so we just do some basic algebra and bounce it around. And so we end up, we'll divide both sides by 2.99. And we get 27.1034 equals x minus 1. Don't need parentheses anymore. Add 1, so we get x equals to 28.1034. And then, like you said, Ryan, your other concern, do we have to round down? X is our number of equal energy users that we support. And this is telling us that we can support 28.1034 equal energy users. And so again, in this sort of situation, we can't support any more than 28 full users. We can't have a tenth of a user. That's something that doesn't matter for our system. We can support 28 people, and we have a little bit extra space if we need it. But we can't support any more than 28. We don't have enough power. We don't have enough received signal power, and there's too much interference power for us to be able to do any more than 28 equal energy users. And so in this case, we would have to round down and say 28 equal energy users. And so that's always the question you want to be aware of and ask yourself with these sort of problems in context, is what is the variable I'm actually solving for. So in this case, it's equal energy users, and you have to ask yourself if you can have partial units. So does a partial user make sense? No, not really. Stephen asked, do you have to convert dBm to dBw? You don't have to. You could, as long as they're the same. As long as you keep your power in the same unit, that's okay, because we end up canceling out and we don't end up with a power calculation. So it doesn't really matter as long as they're consistent, because if you were going to do the conversion, you would have to convert this side and that side by the same number, right? So with dBm to dBw, we'd have to subtract 30 from both sides, but that's balancing the equation. If we do the same thing to both sides of the equation, we're basically not changing the equation. And so it doesn't matter as long as you're consistent. You can't convert one or the other. It's either all or nothing. And again, since we're not ending up with a power unit, we're just ending up with a number of users, it doesn't ultimately matter. You could do, it would just be an extra step, and ultimately for this problem, it's not strictly necessary. Mathematically, it's exactly the same either way, but it just depends what you're comfortable working with. If you want to do everything in dBw just for consistency's sake, you're welcome to. Yeah, and I mean, we can take turns or not. I'm sure if any one person has a question, it's a pretty good chance that somebody else is going to have the same question. So we can take turns if that's how we want to do it. It'll be good to let everybody have a chance to ask their questions. So yeah, let's try to keep it in a rotation of sorts. All right, Stephen proposes question 40. OFDM is a modulation technique, not a multiple access strategy. Is that true or false? So the distinction on this question is, and the confusing part, is that we generally talked about two different forms of OFDM, right? Let me get rid of. So for question 40, let me grab the question text. OFDM is a modulation technique, not a multiple access strategy. Is that true? And so we have two things that we have to keep basically in our heads when we start talking about OFDM. We have OFDM proper, which is orthogonal frequency division multiplexing. That's off the top of my head, so let me verify that that's. But then the other one, let me question mark that one just until I can verify. The other scheme that we have to keep in mind is OFDM-A. And so these are the two different strategies that are very similar, but they are not the same thing, and they serve different purposes. And so because this question is specifically asking about OFDM, which is correct, just double checked it, I am right, all right. OFDM is not a multiple access strategy. OFDM is just the modulation technique for basically transmitting the data. It does not include any methods of how the user accesses the channel. OFDM is strictly talking about how the data is encoded. And so OFDM-A is the multiple access strategy. And Stephen says TDMA or FDMA are multiple access strategies. I think, yeah, that's correct, because those stand for time division multiple access and frequency division multiple access. So those are both schemes where we let the users get access to the data channel. We don't worry how the data is encoded on the channel. We're purely talking about how we let people get access to the data stream. And so that's a similar breakdown with OFDM and OFDM-A. OFDM is how we're encoding the data on the data channel. OFDM-A is basically using similar systems, orthogonal frequency division multiple. OFDM-A is using a similar concept to OFDM, but it's talking about how we break up the users to access a shared channel. And so to answer question 40, OFDM is not a multiple access strategy, so that's false. OFDM-A is the multiple access strategy. Or actually, let me check the text of the question before I say true or false. So the question is actually true, sorry. So OFDM is a modulation technique, not a multiple access strategy. The question is true. Sorry, I forgot which order it was asking the questions. So OFDM is not a multiple access strategy. OFDM-A is a multiple access strategy. So 40, the answer is true. Oops. And like Stephen said, if a couple other examples of multiple access are TDMA and FDMA, and OFDMA is kind of sort of a combination of ideas from both of those prior schools as well. And so those are two terms. OFDM and OFDMA are two pretty easily confused terms because they are fairly similar, but they're addressing different things. OFDM is addressing the data modulation. OFDMA is asking how we can get users, have multiple users share a wireless channel. And that's actually related to question 41, what we were just saying. I know nobody asked for this one, but since we're here, I'll talk about it. Question 41 is asking, in OFDMA, users share blank and blank. And so OFDMA is fundamentally a combination of elements of, like Stephen pointed out, TDMA and FDMA. So for question 41, OFDMA takes advantage of subcarriers and time slots. And so for time slots, that's your TDMA, your time division, because it's letting certain users access the channel at certain times. But then also there's a selection of subcarriers that can be used in order to increase data rate and generally just be more efficient. And that's similar to frequency division, because each subcarrier has a range of frequencies included out of the main carrier frequency. Or out of the main spectrum, I guess I should say, instead of specific frequencies. And so OFDMA is a hybrid of TDMA and FDMA, because you're using frequency blocks, i.e. the subcarriers, and time slots for users to share the channel access. And again, I realize nobody asked about that one, but we were right here, and I wanted to bring it up since it was related. And if you're looking for the book page to time and bandwidth, so I guess I was close. Yeah, you had the right idea, Ryan. It was just a little bit more specific regarding bandwidth. Time would probably be sufficient. If you said time is close, time is borderline. Bandwidth is a little less true because it's a little too specific in the opposite direction. But as I was saying, that's on page 246. If you want to get the book wording on that one. It's basically, OFDMA uses a combination of FDMA and TDMA by allowing different users to use a subset of the subcarriers at different times. So again, I would probably accept time and subcarriers, but time slots is a bit more specific. Alright, Ryan, with question 30. What are the number of frequencies per cell of a TDMA system that has 20 megahertz total bandwidth, single channel bandwidth of 200 kilohertz, and a cluster size of 7? Okay. So for question 30, we have, let me clear out some space here. Ryan did total bandwidth divided by single bandwidth equals channels, and channels divided by number of cells. So there is a little bit more of a specific formula, but you're pretty close. So, let's see, let me grab the question text. You have the right idea for sure. It's just there's a slightly more specific formula. And so what we're looking at here and let me make sure I can pull up the right formula for this one. Give me 1 sec to pull this up. So what we have here is we have number of frequencies per cell equals total bandwidth divided by channel bandwidth times cluster size. And this is the formula that's present in my notes, so I'm going to, once I talk through this, I'm going to go back through and make sure that that's something that you've seen, or if it's not directly like this, how we derive it. So give me 1 second right now. I'm going to just verify that this is correct or clear. Okay, so that's actually a derived formula, so let me walk it back a second. So the core formula that we're looking at is our traffic capacity formula, which is on slide traffic capacity formula. And this is on slide week 6 lecture 10-1, slide 14. And so the traffic capacity formula states that number of frequencies per cell equals total bandwidth divided by the quantity channel bandwidth times cluster size. And so that's the traffic capacity formula given on that lecture slide. And so what now if we plug in the numbers, because we have basically everything we need here and we're solving for number of frequencies, so we can just go ahead and do it. We have frequency, let's just shorten this number, frequencies equals total bandwidth, which is 20 megahertz, divided by channel bandwidth, which is 200 kilohertz, times 7, our cluster size. And so if we do the number here, we have number of frequencies equals 20 million. And again, I'm just converting to the base unit because I prefer to work that way. You don't necessarily have to, you just have to watch your units if you don't. Where's the calculator? $20 million divided by 200,000 times 7. And that gives me 14.2857. And so now that we're here, we run into that problem again where we say, okay, we have a partial number in a word problem or context that might not be applicable. And so how should we handle this situation in regards to the number of frequencies? so Ryan says round down. And so if we look back at the question, what are the number of frequencies per cell of a TDMA system that has 20 megahertz total bandwidth, single cell capacity of 200 kilohertz, and a cluster size of 7? And so in this case, we're given that we have a total bandwidth, a channel bandwidth, and a cluster size. And so we're trying to find a number of frequencies. If we have more than the 14th frequency, then if we round down, would all the other numbers still be the same? Or think about it this way. If we rounded down, would we be able to meet these same numbers? Let me double check this just to make sure I'm on the right track. And Alice says you can't have a partial frequency, and that's true. But in this situation, and again, I'm double checking this to verify, but my first thought would be we'd have to round up. Because we're given that this is our system. We know for a fact that we have 20 megahertz total bandwidth and a single channel bandwidth of 200 kilohertz and a cluster size of 7. And so if we rounded down, I don't think we'd be able to achieve that. So this might be a situation where we have, if we round up to 15, we just have some extra space. Like we don't need all. Let me double check this before I go any further. Because this to me looks like a situation where we would have to round up instead of down, but I need to verify really quick before I give you guys the wrong idea. I can kind of see it both ways. Oops, that's not what I wanted to do. Right, it looks like you guys are on the same page as me, so you need a minimum, Stephen puts it in a good way, you need a minimum of 14.285 to be able to do it. And because we can't have a partial one, you would have to have 15 in order to meet the system requirements that was given out. We wouldn't use 15 to its full capacity, but we would still need to have 15 in order to make it possible at all. Because if we went down to 14, we wouldn't be able to support that. And so I think that would be the philosophy I would take. I'm just seeing if I can double check this and get any specific clarification on it. This isn't a huge part of the problem, but it is worth talking about. So give me 1 second to just see if I can verify this with some other notes. Ryan says sort of like partial bits, and yeah, that was the perspective I was looking at it from. And so again, that's the tricky part with these sort of questions when you're trying to figure out, okay, which of the two scenarios does it work with? Is it either a partial bit situation or is it like a person situation where you can't have half a person? Except in statistics. Give me one more second to see if I can find any cross-reference notes, and then we will move on. Because I don't want to take too much time on this, because this is somewhat minor in the grand scheme of things, but okay, let's move on for now, and we'll assume that we round up. So we need to, again, the reason why we round up is we need that 15th frequency in order for this to happen, because it says we need at least 14.2857 frequencies to make this work. And since we can't have a partial frequency, we just have to step it up to another frequency. 14 is not sufficient because we need 14.2857. And so instead, we need to go to 15. And we're not using those 15 frequencies to their full capacity, or we're not using the 15th to its full capacity, but we still need it in order to make it work, because it won't work with any less than 14.2857. And so we'll move on. I'll keep looking. So the screen is going to go black for a second while I look for those notes, because I know I have them somewhere. But I am still watching, so if you propose another question, we will move on. But I want to look this up for my own interest, if nothing else at this point. Let me check my other notes. Okay, it looks like my other notes are mostly in agreement, at least up to the rounding point, so. Quick question for 14. Okay, yeah, 14. Yeah, 14's kind of out of there. It's a bit of an oddball question, and it's weird to see. So the thing about 14 is that when we look at the two halves of a half-wave dipole, the general structure of what a half-wave dipole looks like. Let me see if I can move this GIF over. So the easiest way for me to illustrate it, my reasoning was like, how could it not have an effect? And yeah, this one was something that hung me up last time too, and hung a lot of the students up. But the tricky thing about this question is a half-wave dipole looks like this. With leg, with leg. So this is what a half-wave dipole antenna looks like. And so what the question's asking you is if you put a plane right here, what effect would that have, if any? Or rather, if it would have an effect or not, is the question. And so the easiest way to illustrate this is not my own work. 1 second. Why recreate an illustration when Wikipedia does it for you? And this is ultimately the illustration that we came around to last time, because I think it does the best visual representation of what we're talking about for this problem. And so we have the half-wave dipole shape, and again, we're asking if we insert an infinitely conducting plane in between the two halves. Well, look, if you look at the blue lines, which is the current, which is basically the power that we're talking about for this problem of the transmission, you'll notice that it doesn't actually touch or interfere. There's nothing happening in the middle for the blue. And again, the blue is what we're looking at because that's where the power is radiating from. That's the current being sent into the air, which is our signal power. And again, there is no current in between the two halves of the dipole. It's all radiating outwards from the arms. It's radiating perpendicular to the arms. And so that means that if you put a plane right up the middle, it shouldn't have any effect on the current. Because again, there's no current flowing in that space between the two waves. Everything's perpendicular to the arm. And so our best reasoning, as we looking at this illustration, and I ended up talking to Dr. Helm about it last semester, is that it won't have any effect if you insert the plane in the middle. Because again, the current is radiating perpendicular to the arms, not in between the arms at all. So if you insert a plane right in the middle here, you won't have any effect on the fields created. Because again, the blue symbolizes the fields being created. Ryan, science is magic, please. Yeah, antennas still lose me. I'm not an electrical engineer. Antennas are still definitely the magic of this whole thing to me. Steven says, what about arc? I'm not 100% sure what you mean by that. If that's a metal, then the electricity should arc. But again, if it's not in an area, we're not talking about the voltage, we're not talking about the current of the wire, because you'll see that the voltage is still crossing in that middle, although I'm not sure how much of a representation that is. We're talking about the power that gets radiated from the antenna. So again, with antennas, when we run current through them, they convert that current, the electrical current, into an electrical field. And so all we're concerned about for the purposes of the fields created by the antenna are the electrical field, not the current itself. And so as far as the field that's created, which is represented by the blue in this image, it doesn't interact with the middle between these two poles at all. And so if we put metal in here, we might get some voltage if we were running enough current, because you're right, it would probably jump from the legs. But that's not what we're concerned about. We're primarily concerned, again, it's one of those physics questions where you have to assume everything else in the system doesn't exist for the sake of the problem. But if we're just looking at the blue fields, then there is no interaction of the fields between the two poles. So there's no electric field created between the two poles, so inserting a metal object there won't have any effect. And again, you're probably right on depending on the distance between them, and like the higher the voltage, you would probably have an arc to the metal plate, but that wouldn't affect the fields of the antenna for the sake of this problem. But again, this is a pretty esoteric problem, and I don't think you'll be seeing something quite like this on the final. This is just to kind of remind you that antennas are a thing, whether or not you understand how they work. Just reminding you that we did talk about different dipoles, quarter wave, half wave. yeah, I wouldn't worry too much about this particular knowledge set. Just remember to review some of your antenna stuff. But this was the best illustration we could find to explain this concept, and I'm sticking with it. Oops. Exactly, Stephen. Just put your finger in between the dipoles, nothing will happen to you. Not something I'm willing to test on my own time, but... Alright, let's get rid of 14, because that's not really... That's about all it is. Either you've seen that image and you get an explanation of it, or you haven't really. And again, that image came from the Wikipedia page for half-wave dipoles. That was the easiest way. Alright, yeah, Al, and again, we're doing this on Sunday again. It'll be at the same time on Sunday. I'm sorry I had to do that, but my schedule changed on Sunday a little bit, but I still wanted to do it for you one more time. So this video will be recorded and available later tonight, and then Sunday will be same deal, 7 to 8 Sunday, available hopefully later that evening. If you're really procrastinating, if you've decided not to do the test by then. But that's your choice, so I might as well try to accommodate. If you have 2 more, Ryan, and Spencer has 1, that'll probably put us close to our 8 o'clock time. So let's try that, see if Spencer has 1, and we'll get your 2 true-false, and then we'll think about wrapping up at that point. Depending on the time, it might be quicker. Steven's got 1 too. Alright. 22 and 47. Okay, we got a couple here, so let's... $56. Okay. Okay, so Spencer has 22 also. So let's see, we have 22, 47, 56. Okay, so we'll go through those 2. We'll do 22, 47, 56, not necessarily in that order, and then we'll see where we're at that point. So we'll start with 56, and then we'll work our way through. So for 56, we are asked... Oops, let's get back to the black font. Ricean probability density function is a Rayleigh PDF with a direct signal wave. Okay, so this is essentially just a definition, but it's kind of dressed up as one. And so if we go to the book and look up Ricean, or Rayleigh, actually, let's try Rayleigh because Ricean just said nothing. I know that's not true. Sometimes the search function in the book is a little odd for... Anyway, okay, so on page 187, yeah, there is also Dr. Helm's lecture, which I have not seen yet. So if this is covered by him, I'll make it quick. But basically, Rayleigh That's not quite spelled right, but ray. Fading occurs when there's multiple indirect paths but no dominant, like, line of sight path. So rayleigh occurs when you don't have a direct path, but you have multiple reflected or indirect paths. Now, Ricean is multiple indirect paths and a dominant path or direct path. And so Ricean is where you have multiple indirect paths, but you also have a dominant path to the original broadcast. And so effectively what it's asking you is if Ricean is the same as a rayleigh, but with the addition of a direct signal, and that's true, because rayleigh is multiple indirect paths, but no dominant path, and Ricean is multiple indirect paths, so it's basically a rayleigh, but it also has a direct dominant path. So for 56, it is true, and hopefully that's the same way Dr. Helm addressed that last night, because that's what I have in my notes and in my book. So that one might need a referencing with his answer, but hopefully that's the same. And then 22 was the next one. Okay. Similar concept. I'll have to double check and see what he said, but that should be the right approach. Okay. And this is on, and so Stephen, I think that was Stephen. Gonna have to reread that several more times until I get this. Thought I had one right. That one's on page 187 of the book. Kind of compares and contrasts Rayleigh and Ricean functions. Again, getting this specific, you probably won't need to know exactly. You don't need to go into too much detail of what Rayleigh and Ricean are, but you may be asked questions about multipath, which might be useful for you to know generally a little bit more about this section. But I doubt anything will quite be that specific going into talking about probability density functions. Just generally keeping an idea of multipath and fading in general will probably be sufficient, but I have to go back and look at what Dr. Helm was saying last night to get to be sure we're on the same page. But if we're ready to move on to 22, then let's tackle that, because a couple people said we wanted that. So to be used in realizable CDMA systems, pseudorandom signals must be constructed from a finite number of random pre-selected parameters. Okay, that's a long one, but there we go. And so let me go back to what Ryan was saying. I know a pseudorandom code is generated, but I don't know if it's from a finite number of random parameters. Okay. So yeah, essentially you have the right idea. You're just wondering about where the original pseudorandom code is coming from. And so yeah, the point with CDMA, we use the PM code, or the pseudorandom number code, in order to more efficiently communicate and share the system. And so let me pull it up here real quick. Let me pull up the PN code. Yeah, my notes just say a modulo 2 process. Okay, yeah. So basically, in the book, if we go back to where PN code is kind of discussed on page 148, it basically just says, binary data are fed into a modulator using some digital to analog encoding scheme, and the resulting signal is centered on some base frequency. A pseudo noise or pseudo-random number source serves as an index into a table of frequencies. This is the spreading code referred to previously. So basically, what the book is saying there on page 148, is that the pseudo-random number serves as an index into a table of frequencies. And so if the PN code is serving as an index into a table of frequencies, if we change what frequencies are available or how many are available, then the index is going to be different, or the requirements of the index are going to be different, right? If our table consists of 1 through 5 frequencies, then our index needs to be able to support 1 through 5 frequencies. If our table of frequencies instead supports 1 to 100 frequencies, then our index is going to have to support a bigger range of numbers. And so that would be part of our pre-selected parameters for the PN code, is that that's one of the potential index or parameters is the table of frequencies, and that would be a finite number. And again, the first part we're pretty sure is true, because to be used in CDMA systems, we need to use pseudo-random signals, and that's constructed from a finite number of preset parameters. And so for 22, we're looking at true. Because we need those pseudo-random signals to ensure privacy. Because again, with CDMA, we have everybody talking, but then you can only receive what your code is synchronized to. But then those randomly generated codes, those PN codes, have to be created from a finite number of pre-selected parameters. And so again, if we're looking at, for our example from the book, if we're talking about an index of table frequencies, then each PN code will correspond to a random frequency in the table. And then that way there's a finite number of randomly pre-selected parameters that the PN codes correspond to. So again, if we have a table of frequencies of 100 different frequencies, we might randomly assign PN codes. So let's say PN code 234 corresponds to frequency 56, for example, for, again, arbitrary example. But that would be randomly selecting a pre-selected parameter. So we've already decided what frequencies we're using. We randomly assign PN codes to it. But overall, it's just generally, to be used in systems, we need pseudo-random signals, and they're constructed from a finite number of pre-selected parameters. That's basically describing PN codes, so that problem, the answer to that problem is true. And then finally 47. And again, that's question 22 is getting pretty deep into CDMA and how PN codes work. You probably won't need to go particularly that deep in the final. It's unlikely you'll get something that's super specific. Okay, so for 47, we have blank has replaced TDMA and CDMA as the most commonly used multiplexing technique in both cellular and Wi-Fi systems. Okay. So this one, luckily, not too many formulas, just book reading. And so, if we remember what we were talking about in the previous problem, or I've already forgotten what problem that is, but when we were talking about modulation schemes and multiple access strategies before, one second, let me get the book to the same page. So the main technology, I gift LFDMA for 47, me too, so you guys are so close. Except this is talking about multiplexing techniques, not multiple access techniques. So we're only talking about multiplexing. We're talking about the data, not necessarily... And again, this is a little confusing because it's talking about multiple access here, but then it's talking about multiplexing techniques here. In fact, you guys are so close, I need to double check this and make sure. Last night, all Dr. Helm said was LTE is phasing out. Yeah, LTE, i.e. long-term evolution. And if you look a little bit deeper past the surface on that one, so, looking in the book, and again, this is, like Dr. Helm was saying, LTE is phasing out TDM and CDMA. That's true. LTE consists of OFDM, OFDMA, and MIMO. So, this one is probably, okay, Ryan's got table 14, page 471. You have a source, so let's see what your source says. I'm not seeing a table on that page. It looks like, from what I'm seeing, that either I would probably accept OFDM or OFDMA. Because again, they're so closely related. Let me find. So yeah, I think I ended up finding it, Ryan. It's fine. I got it. I think either you could get away with saying either OFDMA or OFDM. I might say, since we're talking multiplexing techniques, I think you guys are right. I think it is OFDMA, because this is multiplexing techniques, not modulation techniques. I think when I first read it, I thought it said modulation technique. But multiplexing is letting multiple users get advantage, so I think that's essentially saying the same thing. You can consider multiplexing being the same as multiple access. Because again, multiplexing is just a problem of having multiple users having to share a single channel. So I think OFDMA would be the best answer there, although OFDM would probably also be acceptable, but in the fact that it's replacing TDMA and CDMA, I think OFDMA is the best answer. So I think you guys had it right initially on that one. When I first read it, I thought that said for some reason my brain thought that said modulation techniques, but for the purposes of multiplexing and multiple access, OFDMA is the best answer there, I think. Let's get back down. OFDMA and not SC-FDMA. So the distinction there is, come on. Where are we? I just had it a second ago. So it's true that LTE uses SC OFDM, but because we're talking about cellular and Wi-Fi systems, if we're considering both of them, Wi-Fi doesn't use the SC FDMA. Only LTE does that. However, both WiMAX and LTE use OFDMA. And so, again, it's a case of best answer, and I think OFDMA is the best answer because, and again, this is from page, oops, that went wrong, page 454 says that WiMAX equals OFDMA uplink and downlink, whereas LTE equals OFDMA downlink and SC. It says OFDM here, but uplink. So it's just a case of best answer. I would say if we're talking about WiMAX and LTE, OFDMA is the better answer because SC OFDM, or like you said, SC FDMA only really applies to LTE. But OFDMA has been more important in replacing TDMA and CDMA for both Wi-Fi and cellular systems. Yep, Steven, I know it's late for you, so yeah, no worries. We're probably about wrapping up anyway. We got to the questions that were posed. And yeah, I realize Sunday is probably less convenient for you this week, but unfortunately schedule changes had to adjust that. But yes, I will see the guys then, and then I think we'll wrap it up for today too, since it is right around 8 o'clock. And like I said, we addressed the questions that we had for today. So we will again be doing this on Sunday, same time, same place, 7 to 8. Feel free to take the test before then if you like, but I will be available then for any last minute questions that you have. And again, I wouldn't worry. Some of these questions that we got today were very, very specific, and we're kind of asking you, I don't really, not formula questions, but more like proof of concept, like conceptual questions. And I wouldn't worry about getting too deep into those. They're mostly just posed for you to kind of refresh your memory on the general concepts it's asking you. So like for this one, generally just keeping in mind that the main multiplexing techniques that we're talking about are OFDMA, TDMA, and CDMA. That's kind of the important part, having a general idea on what the distinctions are. So TDMA is obviously time slots. CDMA is frequency slots, or sharing frequencies, or rather not sharing frequencies, splitting users up by frequency slot. And OFDMA is a hybrid of the two, splitting subcarriers per user per time slot. So again, some of these questions get pretty specific, but it's unlikely you'll be asked anything that super specific on the test. Most of the test will be things you've seen before, applications of formulas, and a couple general knowledge questions. But again, it doesn't hurt to be prepared. So doing the studying and getting more familiar with the concepts that you haven't necessarily talked about in a while will help you one way or another. It can only help you. All right, I'm going to give it 1 minute or a couple minutes here just to make sure everybody's good for now. And again, feel free to contribute to the discussion board if you come up with something or some other question that between now and Sunday that you want urgently answered. But other than that, like I said, I'm going to give it a couple minutes here just to make sure everybody's good, and then I will call it for today. So thank you guys for attending, and I will see you. If you haven't taken the test yet, I will see you on Sunday. And if you are going to take the test, then good luck, and it's been a good semester. Be sure to do your course evaluations. It's very helpful for improving this class and improving these sessions, etc., etc. All right, have a good night, everyone. See you later or on Sunday.